Greetings and salutations from the University of Pennsylvania. Broadcasting live from beautiful downtown Philadelphia, I'm Michael Kearns, and this is Networked Life. In this lecture, we're going to introduce some basic definitions and terminology about networks that we'll be using for the remainder of the course. In this course, a network, or as we will sometimes call it, a graph, is an abstract mathematical object. It consists of a collection of individuals or entities that are each called a vertex or a node in the network, and then a list of pairs of vertices that are neighbors or directly connected, representing the edges or the links in the network. Let me give a couple of examples. You can imagine a network in which the vertices represent mathematicians, and there is an edge or a link between two mathematicians if they have ever co-authored a paper together. We will shortly study such a network. Another example would be a network in which the vertices represent Facebook users, and the edges represent Facebook friendships. A more abstract content network might be one in which the vertices represent news articles, and there is an edge between two news articles if they share enough words in common. Networks are powerful, and they can represent any binary or two-part relationship over the individuals in the network. But this may not capture all of the information and structure that there is in the world. For instance, in the example of the mathematicians network, if mathematicians A, B, and C had jointly co-authored a single paper together, that would be captured as three separate edges in the network, one between A and B, another between A and C, and one between B and C. But we would have lost the information that in fact all three authors were on a common paper. It's quite common and often helpful to visualize networks with a diagram, like the one shown down here in the lower right, in which we represent the vertices or nodes by tiny ovals, such as this one, and this one, and the edges or links between vertices by lines connecting them, like this edge here, and this one here. But it's important to remember that in this course, the network is the abstract list of edges, not the particular visualization we might be looking at, and the same underlying network may have many different visualizations. For example, here's a simple network with 1, 2, 3, 4 vertices and these edges. But to us, the network would be exactly the same if instead I chose to draw that last edge going around the long way. The pairwise relationships haven't changed, and therefore neither has the network. Only the layout or visualization has been altered. Throughout the course, we will use capital N to denote the number of vertices in a particular network. What is the largest number of edges that there can be in a network with n vertices? The answer is n times n minus 1 divided by 2. That comes from there being n choices for a vertex to appear at one end of the edge, n minus 1 choices for a different vertex to appear at the other end. We're not allowing self-loops in our definition of networks. And then I need to divide by 2 because in the calculation so far, I've counted each edge twice. Less important than the exact formula is the fact that the number of edges grows quadratically, roughly as n squared divided by 2 in the number of vertices. The degree of a vertex in a network is its number of neighbors or direct connections. So for instance, here's a vertex in this network with degree 3 because it has 3 neighbors. Here's a vertex with degree 2. And here's a vertex with a rather large degree, somewhere in the teens. The distance between two vertices in a network is the length of the shortest path connecting them. That is the minimum number of links or edges that I have to traverse in order to go from one vertex to another. So for instance, again in this network, if I look at the distance between this vertex and this vertex, it looks as if the shortest path between them would take 1, 2, 3 hops. Notice that there might be many other paths that I could take in order to get between two vertices. For instance, I could take this long convoluted path to get between the same pair of vertices. But it's the shortest path between the pair that determines their distance. Also notice that this definition assumes that the network only has a single component or piece. If instead I told you that in addition to what you see here, there was another piece of this network, let's say this little triangular structure over here, then there's no path between this vertex and let's say this vertex, because they are in disconnected components. In the case two vertices are in different connected components, we can think of their distance as being undefined or infinite. In the case, however, that a network has only a single component, we can talk about the diameter of that component. The diameter of a network is the average distance taken between all pairs of individuals in the network, and it's a measure of how near or far typical individuals are from each other in the network. Now, in the discussion so far, we've really been implicitly assuming that all the networks we're discussing are what are called undirected networks. That simply means that the connectivity relationship is symmetric or reciprocal. That is, if vertex U is connected to vertex V, then V is also connected to U. Symmetric connectivity relationships are good models for things like Facebook friendship, where by definition it's not possible for two people to be friends without their mutual consent. But sometimes we'll want to discuss directed networks as well. Examples would include the fact that I can follow you on Twitter without you following me in return, and my web page may point to your web page but not vice versa. In cases like these, the direction of edges matters, and we would typically indicate the directionality in a network diagram by putting an arrow, for instance indicating that the left vertex is connected to the right vertex. This doesn't preclude the possibility that there's also a directed edge in the opposite direction, but it's not necessarily required in a directed network.